Hello everyone. Let's discuss a very interesting question about friction today. The question is whether the work done by friction is path dependent or path independent. To answer this question, we are taking a help of this example where we have a rough path and we have a mass small m, a block small m, which is moving on this rough path. While it is moving on this rough path, we are going to calculate work done and we'll check whether this is path dependent or not. Now let's see. If you just talk about this mass over here, and if you draw the FBD of this mass, the forces acting on it would be gravity and friction. And friction. Let's suppose the particle is moving in this direction with velocity v, so the friction acting over here would be in this particular direction. We want to maintain the velocity v constant, so we have to apply an external force over here, such that this external force is always equal to the friction value, the kinetic friction value acting on this mass. Why is that? Because we want the velocity to be zero. We don't want any kind of acceleration, so that we can just focus on work done by friction. So this is some external force. If we resolve the forces, we'll see that we can resolve mg in the direction perpendicular to this point. How do we know perpendicular direction to this point? We are going to draw the tangent to the path, and this direction perpendicular to this tangent is going to be the direction of the normal. So this is perpendicular to the tangent drawn at this given path. Let's suppose this angle made from x-axis is theta. So over here, this angle will be theta. And if you do a little bit of mathematics, we'll get this angle to be theta. We already know this. This angle is theta. This angle is going to be 90 degree. Gravity makes 90 degree angle from the from the horizontal. If we resolve mg along the direction perpendicular to the surface at this point, this is going to be mg cos theta. And along the surface, we are going to get a component which is in the direction of friction, and that's going to be mg sin theta. For now, we are not worried about mg sin theta component because we want to talk about what would be the normal. Now see that there is no acceleration along the direction perpendicular to the surface at this point. The particle is not moving like this. Particle is only moving along the surface. So we can say let's suppose this is y-axis. This direction, let's assume it to be y-axis. So we can say summation of forces along y-axis to be 0. Why? Because again, there is no acceleration along the normal. Forces along y-axis are normal and mg cos theta, which is 0. N gives us equal to mg cos theta. Now, why is this important? Because we know that the friction value, the value of the kinetic friction is coefficient of kinetic friction mu k into normal acting at the point. So we already have calculated normal from the above equation. We get coefficient of friction into mg cos theta. This would be the value of the friction acting at this particular point. Again, I'll refresh that this theta is the angle or the angle made by the tangent drawn to the surface at this particular point. Now, let us talk about the path itself. Let us consider that the displacement of the particle for this given instant is dr along the surface. So this would be the direction along the surface over here, dr. If we again resolve it along the horizontal and vertical direction, this can be said to be dx and this can be said to be dy. We know that this angle is theta. So from corresponding angle, this angle would also be theta. I hope everyone can see the board. And if we resolve it, we are going to get dx as dr cos theta and dy as dr sin theta. Basic resolution of vectors. Now, if you want to find out work done by friction for this small instant of time or for this small displacement dr, we can simply use the formula F dot dr, where F would be the frictional force, kinetic friction, and dr would be the displacement. We know that direction of friction and direction of displacement are both along the surface but in the opposite direction. Therefore, the angle between them would be 180 degrees. So we get minus cos phi t is minus 1, Fk. And how much is Fk? Mu k mg cos theta into dr. What we can do now is rearrange the formula. So we are going to get minus mu k mg dr cos theta. See over here, we have shown that dr cos theta is equals to dx, displacement along x-axis. So work done by friction gives you minus mu k into mg into dx. See, this part is constant, mu k is constant, m is constant, g is constant, and dx is the displacement only along x-axis. From here, you would have already guessed what the final answer might be. From here, you just need to, for the entire path, if you want to find out the work done, you just have to do the integration. So total work done by friction would be simply integration of minus mu k mg dx, and since we are only talking about x-axis, we are just going to say initial value of initial x position and final x position minus mu k mg would be taken out because they are constants, and we just have to do the integration of dx from xi to xf. Xi is the x component of the initial position. Let's suppose if the coordinates of A can be written as xi and yi, and coordinates of B can be written as xf and yn. Then the motion along x-axis would be only from xi to xf. Integration of dx would be x. So you just have x over here, xi and xf. We can put the limits. Upper limit minus lower limit. This would be displacement along x-axis. So we get this formula where there is no mention of motion along y-axis and the motion is only along x-axis. So with this, what we can conclude? We can see that while we are calculating the work done due to friction, we are only bothering about displacement along x-axis. We don't care about what is happening along y-axis. You could have told me that what if the mass was stopping here? Then also we would have not cared about the displacement along y-axis. We would only have cared about this displacement along x-axis. That's it. Now, one more correction I want to make over here. Rather than saying displacement, we are going to say distance. For an example, let's suppose we have a circular path like this, and a mass is moving on the circular path. Then when it comes back to the initial position, will the work done by friction going to be zero? If we just say displacement along x-axis, then displacement along x-axis is going to be zero. So will the work done be zero? I'll give you a moment to think about it. No, we know that if we move the mass over here, after one rotation, it's going to lose some energy. That means work done by friction is there. Well, friction has taken away some energy from this mass. So rather than saying this is the displacement along x-axis, we are going to say this is distance traveled along x-axis. So we can still say technically that the friction work done by friction is dependent on path, but the path length which is the path length on which the friction is dependent is only the distance along x-axis. So I hope this was enlightening to you. I'll give you a moment to capture the entire thing. Yeah. So I hope this was interesting for you, this was enlightening for you, and this was enriching for you. We'll meet in the next video. For now, thank you.